Okay, hello, welcome to my channel, and this video will be addition to the previous video of how the acceleration vector has been derived, okay, with a little alternative approach. I would say this approach is what I'm uh, more prefer. This basically, so in mathematics, you know that if you have a velocity relationship, if you then differentiate that relationship with respect to time, you would automatically get the acceleration, right? Previously, I showed you how to derive the acceleration vector by graphical method. So to draw axis and then try to summation the vector accordingly, distribute to it on its two component of vector of plus positive theta or positive r. In this case, take a little bit more kind of less geometric complexity. Okay, so uh, fundamentally on the figure shown here, you following from the previous video, you know that the difference in velocity is can be expressed in theta or in r component. Okay, so um, we then make the note of how this vector uh, showing in theta axis and positive r axis. Okay, but if we look on the fundamental of this equation, velocity, the velocity vector expression, okay, you will know that if you differentiated these two this whole equation with respect to time, you would get the acceleration vector, right? And then the vector v will be turned into with the v dot. Then this term will be differentiated accordingly. Okay, so firstly, look at this term. So you would know that if we differentiate it with respect to time, we will get this product here, these two terms. And then this, if we was grouping is like this, you will see that this will be the first of the summation of the differentiation, and this will be the second term. Okay, if we arrange it accordingly to the vector, according to the vector er or vector e theta, vector e r dot, vector e theta dot, you will get this very confusing term. You will get er, vector er, vector e theta that we most familiar with, and vector e r dot that we have derived before, and this vector e theta dot that we have also similarly obtained by the when we derive velocity vector. Okay, so which I recall for you here is what we found when we have when we try to derive the v vector v, is what we get. Then we substitute this knowledge in here, and then in here, then we will get this term. Okay, change it here and here. Okay, after that is a simple mathematics. We just arrange the same term together, er combined with er, e theta term, summation with e theta term, then we will get this expression, and that this expression is the exact identical with the one we previously derived by geometry or graphical vector method. Okay, and that is the beauty of this equation. You don't need to draw anything. Once you have this vector v, you can just differentiate it by time. Just make sure that you differentiate it mathematically correct, then you will get the same expression. Okay, I somehow see this method as more familiar with myself, but of course, to be fundamentally known, I would suggest everyone to watch the previous video to see how it was geometrically drawn, how it was, what is the meaning of each term. That will be give you more understanding. Okay, but regardless of that, which way you prefer is up to you. The important point is to understand how this came from and how you would utilize this correctly. Okay, so if you make it into the end of the video, I say thank you so much for paying attention. Let's see you guys in the next video. That will be the first example of the curvilinear motion. Okay, thank you for watching.